I'm going to give a quick opening and then we will turn things right over to our guest speaker today, who we're very happy to have, Tom Weissmuller. Today we had the inauguration of Joe Biden, an event that I suspect a number of people are not exactly thrilled about, not really looking forward to. And look at the world that this is happening in, one of intense censorship. So Trump is no longer the president, but how are we going to hear from him? Okay, he's been banned from Twitter, YouTube, Instagram, Snapchat, like everything. And that's the president of the United States. So what would happen to a whistleblower speaking up? What would happen to a journalist uncovering a story? How about a candidate running for office, challenging the system the way that Lyndon LaRouche did? What about you? So this is extremely dangerous. And some people say that, well, the First Amendment doesn't apply to these private companies, right? Twitter is a private company. So the phone company is a private company. Can they hang up your calls if they don't like what you're saying? A restaurant is a private company. If I decide in my restaurant that I don't like mixed couples sitting together, can I have a white section and a colored section? I'm a private company. Obviously, I can't do that, right? And how private are these companies? They've all been called before Congress to have Congress yell at them about how they've been allowing Russian disinformation. They have to do more. So Congress is very directly getting involved in these social media companies. But you can always make your own, right? Like Parler, except it was taken off of the store by Google, then by Apple, then kicked off the internet itself by Amazon. Gab, another independent social media platform, has been banned by Visa from taking any payments. So this is the kind of Orwellian, Inquisition type style world that we are entering into. And what is the Biden administration going to do? Well, he had mentioned in his very first speech today at the inauguration that one of his focuses is going to be on domestic terrorism. Now, what is domestic terrorism? On January 6th, some number of people broke into the Capitol. A small portion of the crowds assembled in support of President Trump that day, an even smaller portion of the 75 million some people who voted for him. If laws for domestic terrorism are created, what will they be criminalizing that isn't already illegal? Blowing up a building, that's illegal. Kidnapping people, already illegal. So what will become criminalized? Associating with people who are considered bad? Having thoughts or speech that make you suspect? We do not need domestic terrorism laws. This is extremely dangerous. Otherwise, what's the Biden administration going to do? The military has been told that from now on, drones will be asked for their preferred pronouns before they go and blow up wedding parties. The website to file for unemployment will have rainbow flags on it. And they're going to strive to make sure that communities of all ethnic backgrounds are ripped off equally by Wall Street and London under the Great Reset. So what's this Great Reset? Part of Biden's theme was Build Back Better. This is also the theme that we're hearing from such people who really care about humanity, as the founder of the Davos Forum, Klaus Schwab, I think I got his name wrong, and Prince Charles in Britain, obviously, who cares about the people very much. These people are calling for a great reset of using the calamity induced by COVID to come out of it in a way that they say is stronger and better. Well, how are they planning to do that? What they're saying is that we have such an emergency facing humanity in its entirety, an emergency of climate change, that all the rules have to go out the window. They say that we have to be very strict with our budgets and cut our budgets, but not if it's to shut down carbon dioxide. Then you can do whatever you want. They say that we have to follow the rule of law and democracy. This is very important. Except, they say, if it comes to the climate, in which case maybe you need eco-fascism. Maybe you need a dictatorship in order to impose the changes on humanity as a whole. Already what we're seeing is international institutions are refusing to provide loans to countries that are trying to build their way out of energy poverty by saying that coal-powered plants, no money, no funding. BlackRock, basically the biggest investment fund in the world, richest people in the world, right? What's one of their big focuses? What's one of their big things? Making sure that everything is green, that things are priced by their environmental footprint. Do the world's wealthiest people really care about providing a better, cleaner future for us all? What is the real intention here? We're not going to fully answer that today. That's not the focus. But what I do want to point out is that all of these dramatic and enormous shifts that are being proposed of dropping CO2 emissions by like 50% over some number of decades, these will have a profound impact on our economies, on our abilities to produce and to live well. And all of it is based on a premise that we indeed are facing a cataclysmic emergency, an existential crisis. Just like Nancy Pelosi said that Trump being in office was an existential crisis. He must be impeached. We're told the same thing about climate change, that this is an existential crisis. We have to address it immediately. So I'm very happy to introduce our guest speaker today, Tom Weissmuller. He trained as a meteorologist at NYU, at New York University, and at the Royal Dutch Weather Bureau in Amsterdam. And he's going to be taking us through whether we should be so concerned about a cataclysmic climate change, or what do we really know about the climate. Tom worked for 5 years throughout NASA before, during, and after the moon landings. He's been invited to give speeches at NASA centers. He was highlighted in the American Institute for Aeronautics and Astronautics special issue celebrating NASA's 50th anniversary. And he's a leading member of a group called The Right Climate Stuff. It's a group of former NASA scientists centered in Houston who have urged NASA and the Goddard Institute for Space Studies to refrain from making claims about carbon dioxide without enough evidence. For more than a decade, Tom Weissmuller has traveled the US and abroad, going the extra mile to help people get over their irrational fears by presenting what the real data shows us. His accurate meteorological forecasts are widely followed, and he's spoken all around the world, across the United States, in the Czech Republic, the Netherlands. He spoke to a parliamentary group in China, and he is an expert on the oceans. He chaired a conference panel on the world's oceans held in China. He's shared the platform with Helga Zepp-LaRouche at the National Press Club. He has spoken at many LaRouche Movement events over the years, and we're very happy to have with us today Tom Weissmuller. So Tom, take it away.
All right, I'm going to formally unmute myself. And today I'm going to be talking about really a subset of the climate issues. Basically, the issue of sea level rise. Why sea level rise? This is one of the big existential threats that everybody's concerned about. New York City being underwater and things like that. The fact is, let me, and maybe at some other time, Jason, I can handle and talk about the CO2 issues as far as weather events, hurricanes, tornadoes, things like that. I did not include that in the slide set today, mainly because I don't have 3 hours. I'm going to try to limit this to about 20, 30 minutes. And let's see if we can get some slides up. And I can figure out how to way to escape this a little bit. Good, very good. I'm looking at the wrong slide here. Go back one to the first slide. There we go. Are we confident that satellites are able to measure sea level rise data accurately? The answer is sometimes. So the key is, did we measure, verify, and validate the results of the satellites? Now we have different ways to measure sea level. If I go to the next slide, we use tide gauges, which are placed all over the world. Later on, I'll show you a map of where they all are. But it turns out that the measures of sea level are linear. They're straight line, and yet the tide gauges and satellites don't always agree. Now, how can that happen? And just so I'll throw in, they are not apparently affected by CO2 increases at all. CO2 is going up at a fairly rapid rate, almost exponentially. Sea level rise is still linear. So next slide, please. Okay, first of all, you can tell that the ocean is not exactly flat. This is taken from the bridge of a ship. These are 25-foot waves. It is very difficult to measure sea level from a satellite. But where we are concerned, we're concerned near the shoreline. Very good. Thank you for advancing that slide. This is what a tide gauge looks like. The tide gauge is anchored to the bedrock. It floats inside. They measure a couple of times an hour. Here up in New Hampshire with this particular tide gauges, the tide varies about 8 to 10 feet per day. So the ocean isn't exactly level even up here. But what they try to do is average as best as they can and try to get the results to make sense. Let's go to the next slide. If you would decide to average all the tide gauges, you get a wrong answer. Why? Because people put tide gauges where they're worried about sea level rise. For instance, Norway and Alaska doesn't have that many tide gauges. Why? Because they're experiencing uplift as a result of the last ice age. The rest of the world, sea levels are rising somewhat, meaning that the land is subsiding somewhat. So let's go to the next slide and we'll see how we can measure that. First of all, this particular graphic came from the National Climate Assessment. It's published every couple of years. And the question I have, and even though CO2 is going up, why would sea levels begin to rise now? Let's go to the next slide. Here are some predictions people made. Now this is Gordon MacDonald, who's an author. He's on the Capitol steps. And he's predicting what the sea level is going to be by the year 2020. Well, guess what? It's 2021 right now. The actual rise, he's predicting 6 feet. It's not going to happen. It doesn't even come up to his shoelaces. So that's one claim that you can just throw away. This is James Hansen. James Hansen at the Goddard Institute for Space Studies in 1988 testified to Congress that we were going to get 5 meters of sea level rise, almost 16 feet, by the end of the next century. And we're in that century now. Well, that wasn't happening too quickly. Next slide. So he quickly changed his mind and said, no, it's still going to get to 5 meters, but it's going to go up exponentially. It'll double every 10 years. So if you notice in the graphic, you go to where 2020 is, and whoa, look at that. He's right. Sea level hasn't changed very much. All the change is expected to be in the second half of the century. Let's try the next slide. This is the great oceanographer, Nils Axel Mörner. He's a Swedish oceanographer, probably the best in the world. He passed away about 2 months ago. But he said, there is a limit beyond which sea level cannot rise. And it's at the 1 millimeter a year. The blue area is Nils Axel Mörner's claim as to the maximum possible that it could rise. Now you see that little red arrow on the bottom? It points to a dot. That's where the actual sea level has risen up to 2020. Very, very little. Let's go to the next slide. So there are 3 different sources of data. The tide gauges, they show 1.1 to 1.4 millimeters a year linear, okay? The American satellites, Tropics, Poseidon, and Jason, and it's actually American and French working together, they're showing 3.3 millimeters a year, also linear. Now, I understand lately they've adjusted that down to 2.9 millimeters a year. It's still way higher than the tide gauges. And there's a European satellite, Envisat, which varied between 0.8 and 2.5 millimeters a year. It only flew for 10 years, but it had sub-millimeter accuracy. And we're going to get into that in a minute. Next slide. This is the history of sea level rise for the last 24,000 years. And what happened 24,000 years ago? Well, you can see the great ice sheets that covered the Northern Hemisphere all the way down to Long Island, New York, decided they were going to begin melting. There's a whole lecture I can give on how and why that happened, but they melted, and they melted very rapidly. In the next slide, you can see how quick. All within a 7,000-year period, we had about 120 meters of sea level rise, kind of flattening out as we got to the recent times. Next slide, please. The prediction, and you see that little red arrow on the right side, is that we're going to get 5 meters in the remaining 79 years left in this century. Folks, it's been almost flatlined for 2,000 years. It's not going to go up 5 meters in the next 80 years. Now you can see what tide gauges look like all over the world. They're concentrated in places where there's basically subduction, and people are worried about land dropping. And areas like in Alaska, where land is rising, Norway land is rising, you do have tide gauges, but not that many. But we have a pretty good record, and most of this is Northern Hemisphere, but South America is building on this too. Next slide. This is a concept called glacial isostasy. And you see the green thing there in the middle is a big block of ice, miles and miles deep, pressing down on the oceanosphere. And to the right and the left, you see what is called forebulge, meaning that because the ice is weighing down so much, it actually makes the land rise around where the ice is not. Next slide. This is what the tectonics look like in the Baltic. Now, central Norway had literally 3 miles deep of ice, and now the ice is gone. It is rebounding, and it's rebounded enormously. 800 meters in central Norway. The yellow area shows where there is uplift. The blue area is the opposite of the forebulge. So where the uplift is going, it's dragging down the surrounding land. If you look at the bottom left, that's where the Netherlands is. The Netherlands is sinking. In fact, the oldest tide gauge in the world is in Amsterdam Harbor because they were worried about sinking in the 1600s, and they wanted to measure it. But in between the yellow and the blue part is what I call the zero line. The zero line where there is no uplift and no subsidence. It crosses Denmark, as you can see. We go to the next slide. And there's some real detail. Again, the lower left is where the zero line is. And on that zero line is a little harbor called Slipshaven. If you go to the next slide. And this is the tide gauge at Slipshaven. Goes way back. It's linear, doesn't change, and it rises a steady 1.02 millimeters a year. There's variation. Obviously, the variations are driven by ocean currents, storms, but the general trend lies between those two dashed lines. It's called the 95% confidence zone, meaning that there's a 95% chance that the next data point will lie between those two lines. The green line going up is CO2. So you know the CO2 is accelerated. However, the sea level has not. Let's go to the next slide. So what you What we learned at NASA is that you have to measure, you have to calibrate, you have to verify and validate. The sign in the white is what you see at Johnson Space Center. They put it up before anybody gives a presentation. In God we trust, all others bring data. And the data has to be measured, calibrated, and validated. Next slide, please. So now we got lucky. We have GPS now. And we could put GPS co-located with tide gauges. And that way you can see whether the land is going up and down, and you can eliminate the vertical movement of land. And what you are left with is an accurate measure of sea level. Now, this happens to be the datum for Newland. It's near Cornwall in Great Britain. It is the oldest tide gauge in Great Britain. All the others are keyed to it. Go to the next slide. And you can see the Newland, Great Britain has a subsidence of 7.7 millimeters a year. The sea level rise they're recording is 1.8. You net them out and look at that. You get 1.1 millimeter a year, the same as up in Denmark, where we know it is tectonically inert. Next slide. So here we have, you can see the tide gauges are different colors because of things that are going on. Up in Alaska, we still have uplift because the giant glaciers are gone from Alaska. Along the California coast, we have subduction of the Pacific plate. So you actually have the land going down a little bit. And right in the middle, if you go to the next slide, where that arrow is, we have Prince Rupert in British Columbia. We also have, next slide, Canadian GPS station. Next slide. And at Prince Rupert, there the subsidence is very, very minimal because it's right between the great uplift and subduction. So it's only 0.7 millimeters a year. The rise recorded is 1.17. What's the net rise? 1.1. So, and this is true, again, worldwide in places that are tectonically inert or haven't been adjusted by GPS, validated and verified GPS. Let's go to the next slide. So here's the European satellite, Envisat. Envisat was up there for 10 years. It's like a flying boxcar, full with instrumentation. They focused on sea level rise among other things. The next slide. This shows it what it looked like in the laboratory while they were putting it together. Next slide. Envisat had what's called sub-millimeter resolution. You see the little blue dots on the screen. They represent actual measures. The red line through them is a polynomial regression line. And you notice the variation of sea level is 2 centimeters per year. It's huge. Now, why would there be that much variation worldwide in sea level? Well, you notice, where are the peaks? The peaks all occur during the northern winter or the southern summer. Now, why would that happen? Let's go to the next slide. You can kind of see why. This is what the world looks like during the southern summertime, meaning our winter. It's all ocean. And if you don't have a lot of clouds, what happens? The sun hits the earth. And let's go to the next slide. And that's what it looks like. The ocean is dark. It absorbs the sunlight. The molecular motion increases and you have a rise in sea level. And it's a dramatic rise. And when in the southern, excuse me, in the northern summer, it's over land. And like, if you can back up one slide, to another slide. Okay, you notice the dips are all during our our summertime, meaning that the ocean isn't getting that much heat. So let's go forward a slide or two. There's another concept. It's called the glacial isostatic adjustment. On the left, you see, let's say we'll pick a place that has a lot of ice. Could be Greenland, could be Norway during the great ice ages. The ice itself pulls water to it. It's a gravitational attraction. When the ice begins to melt, in the right of that first graphic, you see that the sea level locally drops, but rises elsewhere. And what the glacial isostatic adjustment tries to do is take that into account. But it really is, I think they're making a mistake here. On the right side graphic, you can see when there's a lot of ice, the sea level is higher. But when the ice is gone, that water has now entered the ocean. The crust of the earth under the oceans is much thinner than it is near land. So you're actually increasing the volume that the ocean can accept in water, and sea level actually drops. So it's basically they're using glacial isostatic adjustment as a correct measure for ocean volume, but not for sea level itself. Next slide, please. So here we have this bunch of satellites compared. The purple line is Envisat. The line on top, the darker blue line, is the American Topex Poseidon adjacent series. Next slide, please. And you notice they're different. Now here's Topex Poseidon. Oh, somehow that end doesn't belong there. It belongs at the end of Poseidon. I haven't figured out how that happened. I'll fix it for the next presentation. They're using two radars. Why are they using two radars? Well, first of all, some radars, like the KU band, which is the more accurate measure, is still measuring only, it has a resolution of 23 millimeters. We're trying to measure 1 millimeter. The C band is actually better in piercing clouds. So they use two radars, and I'm not going to get into the orbital tracking error. Let's go to the next slide. Dr. Roy Spencer, University of Alabama, Huntsville, he had a supposition that if you are flying a satellite over clouds, the resolution gets impaired, which is why you need that KU band radar. Next slide. The clouds are thick. They have billions of water droplets in them. You notice toward the bottom of the cloud, it gets dark because the light just doesn't pierce and penetrate. Let's go to the next slide. They consist of what are called ball lenses, and ball lenses have different refraction properties than, let's say, a regular magnifying glass. A ball lens, if you notice on the top part of that graphic, they actually reflect a tiny portion of light, and the rest goes through and goes to the next ball lens, which is another water droplet. And all the way down, a tiny bit is reflected, the rest is refracted. Next slide. And it refracts at different scattering angles, but most of that light pierces through the ball lens and goes on to the next one. Next slide, please. This is what happens when you have a La Nina year, like we have right now. In a La Nina year, you have a lot of cloud cover over the equatorial Pacific. And again, the Topex Poseidon adjacent satellite, they had two radars, but they only have one antenna. And they had to switch between the two of them. And in order to switch, when the satellite goes over a large cloud, it then uses a band of radar that has poorer resolution. So what do you do? Next slide, please. Here you see the resolution again. You may decide if it's a La Nina situation and you have more cloud cover than usual, what you do is you weight your sea level data toward the C-band because that pierces clouds better. And the KU you use over a clear open ocean. Next slide. This is the key slide. You notice post 92, Topex, Poseidon, and Jason, they go up at a different angle. It's still linear. The red part is the satellite. Now, in 1992, if you were not alive, you have to ask your parents or some of your friends, but did Earth get hit by a meteor? Did our orbit around the sun radically change? Did something really weird happen to the planet that forever changed the direction of sea level rise? Well, Professor Murner and I believe that is absolutely not true. It didn't happen. But why are the satellites showing still linear, and that little dip around 2010 reflects a couple of hurricanes or Walla Wallas in the Pacific that dumped lots and lots of rain on Australia, and the rain replenished the aquifers. It didn't go right back into the ocean. That's reflected in almost every tide gauge on the planet. But the rate of increase is still linear. It's linear, but in a different direction. Now, trust me, I was around in 1992. There was no giant meteor that hit the Earth. Nothing like that happened. So there must be a different explanation. Now, it turns out that someone made a mistake. And the supposition I'm using is that the code used to analyze sea levels added the results of the two radars. And instead of taking an average, somewhere in the computer code, they forgot to divide by 2. And this sounds really elementary, stupid, and simple. Let's go to the next slide. There's a good way that a machine language programmer would compute an average. Now, I used to do machine language computing when I was at NASA. And the old computers we had there in those days could do one thing, and really only one thing. They could add. They couldn't subtract, they couldn't multiply, they couldn't divide. So how do you compute an average if you can't multiply and divide? Well, you use addition. You can take the results of the two radars, KU and C, and that's an addition. Then you can add that result 5 times, and you see that in the next line. And then when the output comes out, don't leave that slide yet, go back. You use a left decimal shift. What you have essentially done, using only addition, you have multiplied by 5 and divided by 10, meaning you have accurately cut it in half. So now we can go to the next slide. So the latest sea level rise estimate was 2.9 millimeters a year. If they did double the radar and not divide by 2, had they done it properly, they would have ended up at 1.45 millimeters a year, knock out the 0.3 millimeters GIA, and look at that. You come to exactly the same as validated GPS measures indicate, 1.15 millimeters a year. Let's go to the next slide. Now, this is the most important slide I'm going to show you probably. Science is not complete when you thankfully achieve the results you were expecting. Now, the people who were analyzing that satellite data were expecting sea level to rise. They forgot to calibrate, verify, and validate those results with the tide gauges. They just didn't do it. They said the tide gauges are wrong, they're too close to the shoreline. Well, of course they are, that's where you want to measure it. Let's go to the next slide. There's a principle called Occam's razor. William of Ockham, he lived in around 1200. And he said, all things being equal, the simplest solution tends to be the best one. Let's go to the next slide. Now, you can make a mistake using Occam's razor too. So here's what some middle school student did on a test. He's asked to find X. Well, that's real simple. He showed where it was. It's not exactly the answer the teacher was looking for. So you can make mistakes using Occam's razor too, but I don't think I'm making one here. Let's go to the next slide. Again, look at the specifications. You realize these were weighted. Averaging makes sense because you cannot get a good, accurate reading with radars that measure at their best 20 times what you're looking, and maybe 50 times what you're looking for. Next slide, please. So here again, you look at the change of direction. If you do that doubling exercise and realize that inadvertently the computer code doubled the result. And by the way, they didn't do machine language programming. That algorithm I showed you earlier was how a machine language programmer would do it. They use a higher level language like Fortran or C or C++, where you can actually tell the language to average. Something went wrong in the code. And either the compiler or the assembler, before the computer even saw it, they forgot to divide that number by 2. The red dot is to where the, the sea level actually is today, and the tide gauges actually measure it there. And the blue dot is even more accurate because you take out the GIA. You notice the blue portion of the graph is titled adjusted tide gauge data. It's not, it's adjusted by the glacial isostatic adjustment. So basically you've had no change in the rate of sea level, even though the satellites are reporting a massive uptick. Next slide, please. Again, measure, calibrate, validate. This is what we did when we were at NASA. And God, we trusted, but everybody else had to bring data. Next slide, please. The fact is, we have records of every tide gauge in the world. They are all basically linear. Some of them are falling, some of them are rising, but they are straight line. Next slide, please. Now, there's some places where things are happening. Here is Seward, Alaska, all right? NOAA says we have a 14 millimeter rise in Seward. That's not true. Seward dropped in a big earthquake in 1964. The trend before and the trend after is linear and actually slightly declining. Next slide. This is the post-earthquake. It's still declining. You notice CO2 is going up. I actually co-authored a paper with the world's greatest oceanographer, Nicholas Murner, explaining in detail what happened to the Seward data. I don't have a link to that paper, but if anybody sends me an email at tom@colderside.com, I can send it to you. Okay, next slide. That's how to find me. That's my so-called contact card. My numbers are on there. And again, tom@colderside.com. If you want a copy of the paper that explains what happened in Seward, or anything else that's relevant. So now I could be open for questions. Now we can get rid of the slide set if we call it back if I need it. And what I'll do is I'm going to mute myself while people ask questions, and I'll unmute myself to answer.
Oh, thank you. So and people could just raise your hand using the hand raising thing there on Zoom. We've got plenty of time for questions, so we should be able to take quite a number of them. And if you have real trouble raising your hand or can't figure that out, you can just unmute and ask your question.
But they can also write something in the chat room and somebody can translate that and send it up. So you can have two ways to ask questions.
I actually had a question, which was, so you had shown how there was the change in the water level that came from the tide gauge itself, and then you use GPS signals to try to account for the fact that if the land itself is moving, that would make it look like the water level is changing. So if you're looking at the land itself moving up or down, it's moving up or down with respect to to what? Like what's the ground zero that you compare things to when you're using these GPS measures to know how much the land is subsiding or coming up?
Well, it's actually, unfortunately, more complicated than that. The Earth has a crust. If you had an apple in your hand, the peel of the apple in relation to the Earth is actually 3 or 4 times as thick as the crust of the Earth. The crust of the Earth is very, very thin. However, we live on it, we walk on it, we call some of it bedrock, makes it sound like it's really very solid. But most of the Earth itself is a high viscosity fluid. Now, but the crust moves and we do things to the crust. Now, I'll give you the best example I can think of. You look down at Florida. In the 1920s, almost nobody was in Florida. Florida became very, very heavily populated on both coasts. What do people need down there? They need drinking water. So where do they get it? They drill into the ground and they extract groundwater. Well, you can take a lot of groundwater. You can take millions of gallons a day out of the earth in Florida. Some of it gets replaced by seawater seeping in. But in most cases, the land just drops when you extract the water. And you have substantial subsidence in Florida as a result of groundwater extraction. Now, all you have to have is an ocean storm or a hurricane coming by, and land that used to be a lot higher is now lower. I think to the tune sometimes of 4 and 5 millimeters a year dropping. And yes, South Beach in Miami now gets flooded a couple of times a year because it has actually sunk. There are other places along the American East Coast which are experiencing a similar thing. The coast of Virginia, 35 million years ago, a meteor hit and busted up the bedrock in the Norfolk, Virginia area. Well, when you have broken bedrock, and I call that frangible bedrock, and you extract water out of it, the land sinks. So one of America's great naval bases happens to be in a part of our country that is sinking. They have to deal with it. They're going to have to build seawalls. It's the adaptive measures that are needed. The ocean itself hasn't changed. In relation to the geoid itself, it's still rising at 1.1, 1.2 millimeters a year worldwide. There are other aspects that you can take into account that affect it. The rotational speed of the Earth. If the Earth rotates faster, what happens is that water will drift toward the equator more and begin to subside near the poles. But that's water moving around the Earth. And again, since we have GPS validation, we can get an accurate measure of the rate of rise anywhere on the planet where you have at least 10 years worth of GPS. And the two that I showed you both exceed 10 years.
Okay, well, a couple of questions, actually several questions came in from the chat already. And if you want to ask your question yourself, raise your hand. Let's go with this one from Brian Romero in Florida. He says that there's reports that Bill Gates wants to spray millions of tons of dust up into the atmosphere to reflect light back and to prevent global warming. What kind of climate or geological impact would it have to squirt millions of tons of dust into the atmosphere, Tom?
Well, he's trying to solve a different problem. Again, Bill Gates and the popular green way of thinking is trying to link CO2 increases to sea level rise. In a longer presentation, I can show you that there is really no relationship between sea level rise and weather events, or sea level rise and hurricanes, or tornadoes, or even precipitation worldwide. CO2 is actually essentially a non-issue. But if you believe that warming the planet is a bad thing, I happen to think warming the planet would probably be very helpful, but that's a different story. And I'm constantly amazed by Canadians who complain that the Earth is getting warmer when they might get a winter wheat crop out of the deal, if in fact it did get warmer up in Canada. But that's a little side issue. I think the kind of geoengineering that throwing that dust in the atmosphere presumes, I think is a very bad mistake. Number one, you can't control where the dust goes. If a jet stream decides to wobble a little bit, it can blow the dust where you don't want the dust to be, like over the open ocean, or over land, or over a desert. The clouds, by the way, La Nina years, where you have a lot of cloud cover over the equatorial Pacific, they do an awful lot to cool the planet because sunlight hitting those clouds bounces off those clouds in wavelengths that CO2 cannot intercept and leaves the Earth, and it gets cooler. Now, we've had a general cooling trend over the last decade and a half. It's still getting slightly warmer, but with much less rapidity than before. Now, you notice in the popular press, you don't hear that much about global warming anymore. You hear about climate change. And climate change is a euphemism for any change in the weather that you believe is bad. And if you're going to try to prevent something that's bad, well, that's a good thing. And you're preventing climate change. And they say by controlling CO2, you can do that. I don't buy into it. There are parts of Africa where you have 18 to 20% more growth because of plant growth being able to handle the so-called climate change of a warming planet. The plants retain their water better. On balance, it's a good thing.
Okay. Stuart, man, you got to do your job a little more there. Okay, so please, okay. So, okay, there's another question that came in that follows up on that one. So you're talking about how Bill Gates is trying to solve the wrong problem. And you're talking about trying to change the climate versus, you had also brought up about what it's like to, you know, to work with it. You had showed how the Netherlands, with the melting of the ice, Norway was coming up, the Netherlands was going down, and that as a result of that, you know, the Netherlands is subsiding. I wonder, do you have an idea about how much the Netherlands has subsided since the, you know, the time that we think of building the dikes and building the windmills? Because the Netherlands is still there and still doing all right, right? Despite this happening, how far has it gone down?
Well, since the last ice age, the Netherlands has subsided 170 meters. Huge. huge, okay? It's gone down a lot. However, in human history, which we've only been measuring it since the 1600s, and I'm talking about a 25,000 year period, okay, for the subsidence, it is generally sinking. The Dutch have been able to keep ahead of it by building dikes, reclaiming land. They're doing a very good job. However, they have to keep adjusting it. Some of the dikes had to be made a little bit higher. There's a natural dune seawall, if you want to use that expression, along the northern coast of Holland that is about close to 90 meters high. Water doesn't get through it, but the places where it dips, the Dutch have put some dikes in. It's well managed. They understand the current rate of subsidence. It's not nearly how much it was when we had that great increase in sea level. And the reason is that over the last, I think you remember that graphic, what they call the Holocene sea level. For the last 6,000 or 7,000 years, it kind of flatlined. And for the last 2,000 years, it didn't, there wasn't that much water added to the oceans. So most of the sea level rise that affected the Netherlands has already happened.
Okay. Another couple questions that came in, and please do feel free to ask these yourself. Okay, I'm happy to ask them from the chat, but you know, you can do it directly too. So here's one that comes from Sebastian Acosta. He wants to know about when the satellites are measuring sea levels, do they have an ability to take into account the changing density of water in different parts of the ocean?
They actually take into account the different density of water vapor in the atmosphere. The radars bounce directly off the ocean surface. They don't have to worry about oceanic density is not a factor in the way the radars work from the satellites. However, the amount of cloud cover that the radar has to penetrate they do have to switch between the wavelengths. They, again, only have one antenna. So it's not as precise as you'd like, but when you have a storm on the ocean, you notice that picture of the storm. I think I led the presentation with that. You have to have a wider footprint on the radar so it can do a better job at averaging between the highs and lows of the waves. That presents some difficulty. Cloud cover, again, is another one. You have to penetrate those clouds. The radar goes through clouds at a slower rate than it does straight down because those ball lenses impair the radar signal on its way down, which is why you need you may have a poor resolution, but you want to have a better cloud penetration on the radars itself.
Sebastian asks, he brings up as an example of different densities in the Straits of Gibraltar, where in other words, how about salinity? Does that have an impact or temperature? Does that have only a local impact on water levels? If it does, how does that fit into global sea levels?
Well, first of all, salinity is dissolved, salt dissolved in the ocean. It will tend to make ocean that is highly salty a little bit higher than ocean without the salt. You also have weather systems that impact it. If you have a high pressure system covering a big part of the ocean actually gets depressed and sea level goes down underneath at high pressure. If you have an ocean storm, like a tropical wave or even a hurricane, it actually lifts the water and pulls it higher. But we're trying to measure sea level in general. You have to adjust for those differences. And the hope is that the radars, in going all over the world, traverse equal number of highs and lows that they will so-called average out. This is not the averaging of the radars I was talking about. That has to be done as a separate calculation. But the signals, in other words, you're never crossing the same ocean twice. The satellite takes about an hour and a half to go around the Earth. And as it does, it crosses new ocean. The pressure, high pressure may be waning, low pressure may be increasing. All that has to be taken into account.
Okay. Vitali has a question.
Yes, hello, welcome. Thank you for your presentation. I appreciate it. As far as I understand, global warming is actually happening, but it's not man-made, right? And there's something that interests me a lot. It's the the movement of the magnetic poles, and I was wondering if that has some sort of effect on just climate change in general.
Okay, that's a neat question because I can get into some real complexity here. I'm going to try to keep it simple. About 15 years ago, a couple of researchers at Columbia University realized that by using dynamite type sounding, they could actually measure the rotational speed of the core of the Earth. Now, the Earth's core is very, very heavy. It's basically iron and heavier metals. And the core, to their surprise, was rotating faster than the surface. Now, why would that happen? And is it constant? Well, at the height of the Ice Age, 20,000 years ago, you had massive amounts of water all over the Earth. Again, at 140 meters worth of water all over the Earth, concentrating on the axis of rotation of the planet, mainly around the North Pole, on land around the North Pole. It's like an ice skater pulling in their hands so they can spin faster. And that's exactly what happened. During the Ice Age, the Earth was spinning quite a lot faster. You had at least 23-hour days, maybe even shorter. But then when the ice melted, the water entered again, equally distributed on the planet. The Earth began to slow down. However, as we are speaking today, the core is still spinning faster than the surface. It is theoretically the differential of rotational speed between the core and the surface is what drives the Earth's magnetic field. We have a phenomenon called the piano key effect. And the piano key effect is measured in places where you have volcanic activity, mainly under the ocean. And what it does, as the lava hardens, it actually solidifies and locks into the magnetic field. So if we examine that lava, we can tell if the poles had been reversed or not. Now, right now, the Earth is still beginning to speed up. Why? Because we are actually depositing more snow around the axis of rotation every winter. Siberia has had record snows, northern Canada has. It's a slight difference, but slight enough so that we don't have to add as many leap seconds as we used to. Now, leap seconds were added in tune with the atomic clock when the Earth was slowing down, but now it's not slowing down that much. It's actually beginning to speed up. At one point or another, maybe, well, I think I predicted mathematically that we will stop adding leap seconds before mid-century. Now that's very significant. at one point or another, in a couple of 100 years, the Earth's rotation will catch up to that of the core. That means the magnetic field will then drop to zero and then reverse. When it drops to zero, more cosmic rays come in because they're not being, the Earth's magnetic field doesn't protect the Earth. Cosmic rays, according to the great Danish meteorologist Svensmark, ends up increasing cloud cover. Why? Because the ionized part of the atmosphere, water vapor condenses on those ionized particles and you have more clouds. Well, guess what? When you have more clouds, the planet gets cooler and maybe another ice age begins. There's a number of Russian researchers who believe that's exactly what's happening now. And we are seeing the beginning of it. But right now we still have a differential. The magnetic poles, by the way, are beginning to wander a little bit because the field is beginning to weaken. As the surface matches the speed of the core of the Earth, it's going to get weaker and weaker until finally they flip. The North Pole becomes a South Pole, magnetically anyway. And we have another key on the piano just placed here. Now, in that slide set I sent you, I have some of those slides if you want me to go into them. But if that explanation is sufficient, hopefully I won't need to do that.
Thank you, I appreciate it.
Looks like the Sanders are up next.
I have one.
Okay. Tom, I would like to ask you about the Little Ice Age because the media doesn't really tell us about that very much, and they pretend it's all just happening. All the cataclysm is happening now, but the Little Ice Age, I think, was pretty important to think about why it happened.
Okay. The Little Ice Age was very important. You had famines in Europe where about a fifth of the European population starved and died. Iceland lost 70% of its population. It was devastating. We had exited what we call the medieval warm period and the Roman warming, where Eric the Red was able to go to Greenland, find lots of grass, raise sheep, have farming on Greenland. They called it Greenland because it really was green. Now, there was still ice on Greenland, but it was not near the coast where the Danes and the Norwegians settled. But then things got colder. They got severely colder, very likely because in the warm period, you had ocean currents going between Norway and Svalbard or Spitsbergen. And those ocean currents melted the floating pack ice. When you melt that pack ice to a certain extent, all of a sudden you have open water on the Arctic. Now the Earth rotates under its atmosphere literally from west to east. So in the Arctic, on all sides of the Arctic, the wind is almost always out of the east. And an eastern wind over an open Arctic can deposit lots of ice and snow on the shores. And that's exactly what happened around 1200. The Arctic had opened so much that it constantly snowed year round around the Arctic shores. The ice and snow that was deposited there reflected incoming sunlight, again, at wavelengths that CO2 can't intercept. And Europe got very, very cold. It got cold in North America too, by the way. We had climate changes here that wiped out entire Indian populations because of movement of the desert as a result of a drier climate. So yes, it was very serious. And then we had a little mini ice age around the 1800, around the time of the American Revolution. When Washington was able to cross the Delaware, he was lucky because the Delaware tended to be frozen at that time. Napoleon was forced out of Russia in 1812, due to a brutal winter, here in this country, they called 1813 and 1814 the years without a summer, because it snowed in every month of the year at one point or another. I'm not talking about, like, say, 6 or 8 feet of snow in the middle of June and July, but enough to kill crops, to make life very, very difficult. And then finally, as the industrial age got into gear, we started getting out of the ice age. Now, I want to be careful. I don't want to become misquoted. CO2 and output from the industrial age contributes to global warming, but it doesn't cause it. There's a saying that correlation is not necessarily causation. It happens to be that the Little Ice Age ended. Why? Because the Arctic Ocean froze over. The Little Ice Age was a result of an open Arctic. Once you sealed the Arctic, there was no more added snow and ice coming down on Northern Europe, and things were able to warm up. Right now, we are experiencing every year a slightly more and more and more open Arctic, which means the Russian scientists who believe that the Earth is going to start getting colder, I happen to believe that they're right. Sorry, long answer to a short question, but you know.
I knew that. Let's see.
You know, this sort of raises the question about how good it is that we've increased our independence from the weather and from our surroundings, like over human history. Like if there's no rain, well, maybe we can pull water out of the ground. We can dig wells. We can build dams to keep it for a drier period. You know, we can build a greenhouse and we can grow crops even, you know, if it is snowing outside, and use electricity to keep them warm. So it's just, it makes me think of that thing about the Netherlands again, that so much of the proposals that are made around the worries people express about climate change are around trying to, you know, dramatically shut down CO2 production, instead of looking at, okay, well, what's, you know, how do we continue to develop our power overall to increase our independence from whatever nature happens to be doing, which is what we've been doing as long as we've been people, I think.
Well, keep in mind, human beings are the only species that can literally change their environment. Other species on Earth react to their environment. If they're not mobile, and all of a sudden you get a little ice age, they simply die out. We don't have woolly mammoths anymore. They weren't adaptable enough and couldn't move south far enough during the Ice Age period. They were adapted as best as they could, but they were out of luck. Insects, they can fly, they can move, but we can actually adapt. We can stay in the same place and make a comfortable environment for us. No other species can do it. We are the only true adaptable species on the planet that is not forced to move. Like you say, we can drill into the ground, we can get water, we can use energy to change things. We can build dams to generate electricity. How many elephants can build a dam? How many gazelles? How many rats? How many roaches? There aren't any. We are it. We are the best. We're using our brain to adapt to our environment, as opposed to changing the environment, which is what these proposals like Bill Gates and other people are trying to bring about. Curtailing CO2, by the way, just for people's information, throughout history, CO2 has not caused a temperature rise. CO2 rising and falling has followed temperature rise and fall. It is what's called a lagging indicator. And why would that be? Well, we know there's a lot of CO2 dissolved in the oceans. When the oceans get warmer, and they do get warmer, they kick out the heavier dissolved CO2 molecules. When the oceans cool down, they allow CO2 to be absorbed more in the oceans. So you have a drop in CO2 following a drop in ocean temperature. And you have a rise in CO2 following a rise in ocean temperature. Yes, we contribute a little bit to that by adding some more CO2, but the contribution is very, very small.
Okay, let's go to Vitali, who has another question for you.
So there's the regular year, and there's something called the great year, which I believe is referred to as the precession of the equinox. This takes about 26 years, 26,000 years, the wobble of the planet. And I was wondering if that has, alongside with what I mentioned before, the magnetic pole shifts, if that contributes to sort of recurring ice age, global warming, global cooling, global warming.
Well, you use exactly the right word. Use the word contribute. It doesn't cause it, but it does contribute it. And the precession of the equinoxes roughly is a 26,000 year cycle. The ice age cycle tends to last about 140,000 years. So you have a number of precessional changes within that, and they are actually reflected in the ice core data that we got at the Vostok ice cores in Antarctica. Now, Antarctica is a stranger place. The Russians have this, this research center in East Antarctica. East is the same name in Russian as Vostok. And through dynamite soundings, they realized that 2 miles under the ice, there was an unfrozen lake, not exposed to the air at all, probably warmed up, if you can use that word when it's 30 below zero, by volcanic tectonic activity. So the Russians said, hey, after Lysenkoism died, and that's a whole other story, hopefully you know what that is, they said, we're going to make our contribution to biology. We're going to drill into that lake. And we're going to go all the way down. We're going to pull out some primordial bacteria and study it. And the Americans who were sharing that base with them said, hey, why don't you do what we did up in Greenland? We took ice cores when we went down. And that gave us a record of snowfall and things. And we can learn a lot from that. So just don't drill into the lake. Use sterilized drill bits and stuff like that so you don't contaminate anything. But make an ice core record. And they did that. It took them 10 years to do that. And those 10 years showed 4 distinct, huge ice ages where sea level dropped 140, 150 meters worldwide. Then there was the east coast of the United States in the great ice ages was the continental shelf of North America. It wasn't where we are today. You could walk out hundreds of miles and still be on dry land at the height of the ice age. And all that was recorded in what is called the Vostok ice core data. Well, later on, the Europeans wanted to upstage the Russians a little bit. The Russians, when they hit the lake, couldn't go any deeper because there was no record in the water. They did get out the bacteria, and some people complained they probably contaminated it with their drills, but that's a whole other story. So the Europeans decided to use the European project for ice core accumulation called EPICA. They went into a different part of the Antarctic with no lake. They have now drilled through 11 separate ice ages. Ice ages, warm periods, ice ages, warm period. We are still today not at the peaks of those warm period, they're called interglacials. We're in an interglacial right now, but we still have a couple of degrees left in temperature rise. And again, before the Arctic Ocean totally opens up. And once it opens up, you have the onset of another ice age. Two American oceanographers and geologists, Ewing and Dunn, figured this out in the 1950s. Wrote a number of articles. And this is way before ice coring. They had no idea what was under the ice. And the ice cores basically validated what Ewing and Dunn surmised. But an open Arctic is needed, and the only way the Arctic is going to stay open is by those ocean currents going up between Norway and Spitsbergen. And by the way, that sill is only 100 meters deep. When you go down 140 meters, no more water gets into the Arctic. And the Arctic flash freezes over, and all the ice can do is melt. And it does. And deep is the ocean, and the cycle begins again.
So I'm a little bit confused. Are we expecting a period of a grand cooling or a warming? And what is it that the geoengineers are trying to do? Prevent a warming in order to prevent a cooling, or kind of get murky?
Okay. The geoengineering at this point and the Paris Climate Accords are all trying to, quote, prevent warming. They're trying to eliminate CO2 if possible, and they will end up creating a cooler planet, but they cannot stop the ocean current from going in between Norway and Spitsbergen. Now, there have been proposals to geoengineer a dam there. The Dutch have done that. A part of the outflow of the Rhine, the Dutch have a dam that you can open and close. And they can decide, yeah, we'll open it 1 year or close it another year. It's basically prevents ocean storms from flooding the Netherlands. They had a terrible flood in 1952, and they said, we're not going to do that again. During the war years, by the way, nobody was building dikes. The Dutch kind of fell behind. And that's why they did that. Now, if you do that for the ocean currents going to the Arctic, you can control if the Arctic is open or closed. Now, the Chinese want to keep it open. Why? Because they're sending container ships through 2.5 months of the year over the open Arctic from Qingdao, China to Rotterdam in the Netherlands, which is basically the commercial gateway to Europe. And a couple of years ago, the Chinese bought the largest container port in Rotterdam just to make sure they can keep doing that. It saves them millions of dollars in container shipping by going over the pole. And the pole, the open polar sea is becoming more and more open in general each year. So I don't think the Chinese want to have the polar sea to freeze over at all. So there's going to be some pushback on some of this geoengineering. You know, we're living on one world. There's conflicting motivations. We have to figure out a way to talk to each other and internationally work with each other to make sure that we have a thriving planet with enough power for everybody. I'd love to see Africa develop a grid, which they don't have right now, like we have in the United States, like Europe has. China is in the process of making a nationwide grid throughout China so that everybody can share the benefits of electricity. That's the kind of things that we need to do in the so-called third world.
You know what, there's a couple more questions that came in, but I think we ought to, well, I'll just pose one of them to you and you can work it into wrapping up. And this will be your chance to offer your concluding thoughts. Sebastian asked another follow-up question about regional differences in sea levels. He asked about whether sea level could have any particular change or local disturbance in, for example, the Bermuda Triangle area. Do atmospheric changes have an ability to cause local sea level changes?
Well, the answer to that is yes. And I think I covered that before. If you have a lot of storms going through the Bermuda Triangle, you're actually going to be raising sea levels because the pressure is lessened. Bermuda itself has never been inundated and is likely not going to be. However, you get the wrong kind of hurricane going in the, near Bermuda, you're going to have some flooding there. The Bermuda Triangle just happens to be a place that it's open ocean. Before we had radars, before we had satellites, there could be a hurricane forming in the Bermuda Triangle and we'd never know it. You wouldn't have any idea. The Great Hurricane of 1938 did exactly that. It formed in the Bermuda Triangle, got really strong, barreled into Long Island and Rhode Island, and caused massive flooding, and everybody was surprised. We did not know what was coming. We had no reports from ships because there aren't very many shipping lanes in the Bermuda Triangle. So it was a very dangerous part of the world insofar as hurricane development was concerned. But there are other things. There is research being done right now about the building of dams in Ethiopia and Sudan, because that the lake behind the dam adds a moisture source, which actually will create more rain in Ethiopia, add more water to the Nile, but then the dam prevents that water from going down to the Nile. And there's all kinds of negotiations and conflict avoidance possible as a result of the dams that the Ethiopians are building. I think it can be a general positive, but it has to be handled politically between the nations in that area. Now, what is one of the consequences? More cloud cover over the western coast of Africa. That's where the hurricane easterly waves begin to form. If you have more cloud cover, you have a weaker hurricane that will be developing, and a weaker hurricane isn't as affected by the Coriolis effect as a very strong, powerful hurricane, because the rotational speed is much less. So a weaker hurricane can make it all the way across and hit the American East Coast. We've had the opposite for the last decade. We've had very few hurricanes hitting the American East Coast. We've had them forming in the Gulf, but that's a different phenomenon. That's due to La Nina and El Nino. But now, as that lake gets formed, and it already exists, we could expect, in general, to see more hurricanes hit the American East Coast. And that's not going to be a very good thing from a damage standpoint. So we have to, again, we can adapt, we have to harden, we have to know what we're doing. I'm very worried about our naval base in Norfolk because it is on land that is subsiding and subsiding rapidly. A major hurricane coming into there could do an awful lot of damage. Hurricane Sandy did a lot of damage in New York City because it was blocked in its northward route by a high pressure system. So it made a quick left turn into New Jersey, and the wind around the hurricane is counterclockwise. It drove water into New York Harbor, and we basically doubled the sea level in lower Manhattan from where it normally would be. And then again, you end up flooding subway tunnels and stuff like that. But that was because the hurricane got stuck there. Hurricane Harvey off the coast of Houston also did the same thing. It got stuck by a high pressure cell and just dumped rain and rain and rain and did a lot of damage through flooding.
Thanks, Tom. Is there anything else that you'd like to say in conclusion tonight?
Well, one of these days, I'll directly address the CO2 problem, meaning CO2 and whether, are there more tornadoes, are there more hurricanes? What's the relationship of CO2 and temperature? You know, I mean, I'm not the only person who's going to present on these events, but I'd be happy to set up a presentation that focuses more on CO2 and meteorology than on sea level rise and oceanography. You let me know, just give me some time to prepare slides. And again, you have my email, Tom at, actually it shows up in my little thing here, Tom at wysmu.com is an easy way to get me. If you have a question or you want to have a copy of that paper on Seward, Alaska that I co-authored with Nils Axel Murnal, let me know and I'll send it off to you. You know, I've presented at Schiller events a number of times. It's a good, intelligent audience, and I appreciate that. The questions we had tonight were superb. You know, they were on point. They didn't digress from what I was talking about. And I rambled on, as I tend to do, because climate is an inordinately complex. It's not simple. You can't just say, hey, we'll stop doing CO2 and everybody will be happy. Things don't work that way.
Well, thanks very much, Tom. I'm sure we'll be looking forward to having you back for that follow-up presentation. And I'll just make a couple of announcements to people who are on right now, which is, one is about an event, another Schiller Institute event coming up on Sunday, which is a celebration of Robbie Burns, the national poet of Scotland. You've probably sung Auld Lang Syne at some New Year's party, but what do you know about the poet who wrote that poem, about his role in the American Revolution, and about how Robbie Burns embodied the ideal of being both an artist and a person of politics, an artist and somebody taking charge of the direction of your society. That'll be Sunday at 6. The registration link is in the chat there. If you miss it, you can look for it at the Schiller Institute New York City Chorus. That's the hosting organization where you can find out about that. And coming up from the LaRouche organization with our future events, given the enormous push that's going to be put on the Green New Deal or something of some name like that, we're definitely going to be continuing going through how the Great Reset plans for what is called by central bankers regime change, that is overthrowing the role of government in creating policy and acting more directly from the central banks themselves, how that lines up with the push for really insane ideas about supposedly combating climate change, which mostly revolve around using incredibly inefficient and expensive and unreliable power sources, and you know, such as these windmills and solar panels, and also how major projects are stopped from the standpoint that they might change the environment, which would supposedly be very bad. One example, just to follow up on Tom on what you brought up about the Ethiopian Renaissance Dam, which is causing debates in the area about how fast you fill up the dam. If you fill it up too quickly, then the Nile isn't going to have enough water. Well, one of the other ideas on this is to drain out some of the swampland in Sudan, where there's, you know, a lot of the water evaporates and is lost to direct use from the river. But that's the kind of thing that environmentalists would say, oh, no, no, no. If you clear out this swampland and have the river move more directly through it, that would be changing nature. That's bad. Whereas really you're saying, where do we want to use this water? Do we want to have this in farmland or in a swamp? You know, so okay, so those are some of the things that we've got coming up, and I think that'll wrap it up for this evening. Thanks again, Tom. Thanks to everybody who asked questions. This was this was a lot of fun. Thanks to everyone who participated, and see you next time.